Welcome everybody to the next video in our series on probability and statistics. I am Dr. Lathram, and today we will continue with our discussion of the gamma family of distributions with part 3 of our series, where we'll talk about the Chi-Squared family. Now, the gamma family is actually related to the Gaussian family in a pretty natural way. That the family of distributions that we'll see where they meet the Gaussian family are called the Chi-Squared family of distributions, and they will be very useful when we're beginning our discussion of inferential statistics. And so just to begin with the theorem, if z has a standard normal distribution, then the square of z will actually follow a gamma distribution with parameters 1/2 and 2. And so how will we go about proving that? Well, we can prove that using moment generating functions. So the moment generating function for z squared is given by the expected value of e to the t z squared. Well, if we plug that into our standard normal probability density function, then we get 1 over the square root of 2 pi times the integral from minus infinity to infinity of e to the t z squared times e to the negative z squared over 2 dz. Well, if we combine the exponentials together, then we see that we have e to the negative 1 minus 2t z squared over 2 dz. So we do a u substitution, and in doing the u substitution, we are able to take out the 1 minus 2t, so it comes out and we get a square root, 1 over the square root of 1 minus 2t, and what we have left over is really the integral of our standard normal distribution. And so what happens, that just integrates to 1, and so we have a moment generating function of 1 minus 2t to the negative 1/2. Now, to recall our moment generating function for the gamma family, it was 1 minus beta t to the negative alpha. And so we can recognize what we just discovered, the moment generating function of z squared, as being having the same moment generating function as a gamma distribution with parameters 1/2 and 2. And then, because the moment generating functions uniquely determine the distributions, then we actually do have that z squared is distributed according to a gamma distribution with parameters 1/2 and 2. And so now let's define our chi-squared family of distributions. So we say that a random variable has a chi-squared distribution with new degrees of freedom, and we denote that with the chi-squared with nu, if it is a distribution of the form gamma with parameters alpha equal to nu over 2 and beta equal to 2. Now, an important property of these chi-square random variables is that if we have some independent chi-square random variables, then if we sum them together, that actually stays still within the chi-squared family, and that the number of degrees of freedom just get added together. And so if x sub I has a chi-square distribution with nu sub I degrees of freedom, and they are independent random variables, then if I add them together, I get a chi-square distribution with a sum from I equals 1 to n of the nu sub I degrees of freedom. So let's see why that might be true. So since each of the random variables has a chi-squared distribution with nu sub I degrees of freedom, then the moment generating function is just given by 1 minus 2t to the negative nu sub I over 2. Now the variables are independent, so the moment generating function of the sum is just going to be the product of the individual moment generating functions. So if I multiply all of those moment generating functions together, I've got 1 minus 2t to the negative nu sub 1 over 2, 1 minus 2t to the negative nu sub 2 over 2, all the way up to 1 minus 2t to the negative nu sub n over 2. When I multiply those together, I can combine the exponents, and so I get 1 minus 2t to the negative sum of the nu sub i's over 2. Now, we will recognize that as also being a member of the chi-squared family, with the number of degrees of freedom being just the sum of the individual degrees of freedom. So to kind of continue with that, if x sub 1, x sub 2, all the way up to x sub n are identically distributed independent random variables, so independent identically distributed, so IID random variables, with x sub I being distributed normally with parameters mu and sigma squared, then if I do this transformation on them and I do x sub I minus mu over sigma, I square all of those, add them together, then I get a distribution that is chi-squared with n degrees of freedom. And if I average them, subtract mu and divide by sigma over root n, then the square of that is distributed with chi-squared, distributed as chi-squared with 1 degree of freedom. Now, how does the proof go for that? Well, since x sub I is distributed normally with parameters mu and sigma squared, then x minus mu over sigma is distributed standard normally. And so if it's distributed standard normally, then the square is then distributed as a chi-squared with 1 degree of freedom. And so from our previous theorem, if we add a bunch of those together, then we get a bunch of chi-squared with 1 degree of freedom. Then we get a chi-squared with n degrees of freedom, where we're adding n variables together. And then for the second conclusion, if we average those values, so now think back to our discussion of the Gaussian family, then probably one of the last theorems that we discussed was the was a noise reduction theorem, in that if we average a bunch of samples, then that average is distributed normally with the same mean, but now the variance is dropping by a factor of 1 over n. And so x bar minus mu over sigma over root n is distributed normally, standard normally. And so the square of that is then going to be distributed with a chi-square distribution with 1 degree of freedom. All right, so now the next theorem, if we have x1, x2, all the way up to xn, and that is an independent, identically distributed sample, so an IID sample from a normal distribution with parameters mu and sigma squared, then x bar, so the average, is actually going to be independent of each of the random variables x sub I minus x bar. Now that seems kind of a strange thing, so let's see why that might be true. Okay. Now the x sub I are independent, and so we know that the joint PDF is going to be a product of the marginals. So my joint PDF then is just going to be kind of a long product, as you can see here. Now what happens, I can combine all of those exponentials together, and so I get an expression that has this form to it. And now I want to do a transformation. So the transformation that I want to do I wanted to find a series of new and random variables where y sub 1 is just going to be my average of the x sub I, so y sub 1 is going to be x bar, and y sub j is going to be x sub j minus x bar for the j going from 2 up to n. And so now, in order to find the new joint PDF for the y sub j's, we actually need the inverse transformation. And so what we can see immediately is that if y sub j is going to be x sub j minus x bar, then y sub j is going to be x sub j minus y1, because y sub 1 was just x bar. And so x sub j is just y sub 1 minus, or y sub 1 plus y sub j. And so that's going to hold for all of the j values from 2 up to n. Now for y sub 1, we got to do a little more work. So for x sub 1, we see that n times y sub 1 is going to be equal to x sub 1 plus the sum from 2 up to n of the other x sub j's. So summing the x sub j's, we find that that's actually going to be equal to y sub 1 plus y sub j, which, or summing from 2 up to n, gives us n minus 1 times y sub 1 plus the sum of the y sub j's from 2 up to n. And so if we want to solve for x sub 1, so we're able to do that, and we find that x sub 1 is going to be n times y sub 1 minus this expression that we had for the sum of the x sub j's, which then simplifies to y sub 1 minus y sub 2 minus y sub 3 minus y sub 4 all the way out to minus y sub n. And so kind of writing our inverse transformation kind of all in one piece, we see here that we have x sub 1 being y1 minus the sum of the other y sub j's, x sub 2, y sub 1 plus y sub 2, x sub 3, and so on. And we get x sub n is equal to y sub 1 plus y sub n. And so if we kind of rewrite each one of our squares, we can make the substitution. X sub 1 minus mu quantity squared. We'll substitute in our expression, and expanding those out, we get a series of expressions of this form. Now that's a lot of algebra to go through. I encourage you to kind of pause the video, work through some of those for yourself, and convince yourself that yes, that algebra actually is true. And so when we sum all of the squares of the x sub k's minus mu's together, we get another really long expression for the y's. Again, that's a lot of algebra, but work through it and convince yourself that it's true. And so that the sum of the x sub k's minus mu's from 1 up to n just simplifies to this expression. And so if we plug that into our exponentials, then what we are able to do is to separate out, using the properties of those exponentials, an exponential that involves y1 minus mu and none of the other y's, and a second exponential that involves y2 up to y sub n's, but does not involve y sub 1. And so that's kind of the super important thing that you're noticing in these expressions, that we were able to make that separation. Okay, so this gives us a substitution that's a product of a function of y sub 1 and another function of the remaining variables, y2 up to y sub n. That's what we just saw. Kind of the last thing that we need for our joint density function is the Jacobian of this transformation. So recalling that the Jacobian is just going to be the partials, and it will, going back to how we had everything written before, we see that our Jacobian actually takes this form. So that's our Jacobian matrix. Now if we want the determinant for n equal to 1, we see that we get a determinant of 1. For n equal to 2, we get a determinant of 2. For 3, we get a determinant of 3, and you're kind of seeing the pattern here, and so we'll claim that for arbitrary n that we get a determinant of the Jacobian of just being n. All right, so we need to determine, we need the determinant of j, and so in order to verify that claim, we need the definition of the determinant. And so for an n by n matrix A, with entries A, capital A sub ij, the determinant is calculated according to, it's a sum of a bunch of products. And so the products, the sum will be taken over all possible permutations, so all possible arrangements of the n elements from 1 up to n. Now this minus 1 to the sigma is the sign of the permutation. That is, if it's 1, if the permutation can be written as a product of an even number of transpositions, and minus 1 if it can be written as an odd number of transpositions. Now that is quite a definition, and if you've not seen determinants discussed in this way before, I would encourage you to go look at a good book on linear algebra, or maybe a good book on abstract algebra, in which they go through a discussion of permutations, and in particular the sign of a permutation. And so if that's not familiar, well, kind of hang with us for just a little bit while we discuss these determinants, and you can come out the other end with us as well. So just hold on just for a little bit. So writing out our definition of our determinant, we have this sum. Our determinant has this form that we see. And so now if we've got particular permutations, if in our permutation, so if in one of the terms of our sum, sigma of 1 is 1, then for all other possible values, if I want to choose a non-zero entry, the only way to do that is to choose it along this diagonal element, because everything else is going to be identically 0. And so what that leads to, if the first entry is 1, then, so if I make the first entry of my choice is 1, then every single other one also has to be 1. And also, in my first row, if I choose some other value other than 1, then for the kth row, the only way to choose that non-zero value is to choose the entry in the first row, or the entry in the first column. And so likewise, if j is not 1 and j is not k, then the only way to choose something that's not going to be 0 is by choosing the element that's along this diagonal. And so what this leads to is that the only permutations in that sum of our determinant that give a non-zero value will be the ones where it is either a transposition, so 1 gets switched with k, or I actually have the identity permutation. And so what that means is that my sum will either, the terms of my sum will either have the form 1 or minus 1 for the sign of the permutation, and then minus 1 as the entry where I switch along the kth column. Everything else has to be 1. And so the punchline of all of this is that we are adding together a total of n minus 1 transpositions of the form 1k and 1 identity. So we've got a total of n ones, and so our determinant just happens to be n. Okay, so if that discussion was a little bit strange and a little bit weird, don't worry about it. You can just take that as kind of a given and make a note of, permutations and determinants and signs of permutations. That's something that I should go and look up a little bit later. So anyway, you can just take that as given. We just throw that extra little bit in there. And so what happens, our joint PDF for our new variables y1 up to yn just looks like n times those two products that we had before. So one expression involving only y sub 1 and another element in the expression, another element in the product that only involves the y2 up to y sub n's. And so what we've done now, we have written our PDF as a product of a function only of y sub 1 and the remaining variables of y sub 2 up to y sub n. Now our limits for our variable y sub 1 are independent of the limits for of the other variables, and that goes the same the other direction. The limits for the y2 up to y sub n's are independent of the y sub 1. And so what that means, that the joint PDF for y sub 1 up to y sub n is actually a product of the marginal for y sub 1 and the joint PDF for y2 up to y sub n. And so, finally getting there, that y sub 1 being x bar is independent of the other variables y sub j being x sub j minus x bar for j going up to 1 to n. And then finally our last step, notice that this identity, that if we add together x sub I minus x bars, then this sum will be identically 0. So again, take some time, write that out, convince yourself that that's going to be true. And so what that means is that we can write x sub 1 minus x bar as the negative of the sum of the x sub j minus x bars for j going from 2 up to n. And so what that means is that even x sub 1 minus x bar can be written as a function of the x sub j minus x bars for 2 up to n. And so we do totally have x bar independent of any of the other random variables x sub 1 minus or x sub j minus x bars. Now that on the surface that may seem like, okay, why exactly did we prove that? That is going to be a major step in a theorem that we're going to see in just a second, and a theorem that we're going to get a lot of mileage out of when we start talking about our statistical inference. All right, so now let's see if we can begin to reap some of the benefits of all of that work. So if we've got x sub 1 up to x sub n are independent, identically distributed, normal random variables with parameters mu and sigma squared, then the sample mean and the sample variance are independent. So we already know that the x bar is independent of the x sub I minus x bars. And so the sample variance, which is written as the sum of the x sub i's minus x bar squared times 1 over n minus 1, that's our sample variance. That is only a function of the x sub I minus x bars. And so the conclusion then is that x bar is independent. So the sample mean is independent of the sample variance. And so now we have a little bit of an algebraic lemma that's sitting before us, that if we have random variables x sub 1 up to x sub n, then if we do a transformation x sub I minus mu over sigma, we square all of those, add them together, we can express that as a sum of the sample variance and an expression involving the sample mean squared. And so adding those together, so we can just take out the sigma squared. That means we're adding up the x sub I minus mu quantity squared. And so kind of the standard algebra trick, we add the mean, subtract the mean, or we add the sample mean and subtract the sample mean inside. And so if we expand that and square each one, we get a term. We get terms that have this form to them. Now, again, kind of using that identity, if we add the x sub i's minus x bars all together from 1 up to n, then that's going to give us a sum of 0. And so what happens in this middle term, that middle term all cancels out, so that's a 0. And what we're left with are just the outside terms. So x sub I minus x bar squared times 1 over sigma squared. And this expression where we have x bar minus mu quantity squared times n over sigma squared, this expression is our n minus 1 times the sample variance squared. So that's our first term. It's n minus 1 times the sample variance divided by sigma squared, plus x bar minus mu over sigma over root n squared. And so now let's see kind of where we were going with that and why that might be important. And here we go. So if we have x sub 1, x sub 2, all the way up to x sub n, our independent, identically distributed random sample from a normal distribution with parameters mu and sigma squared, then the sample variance, properly normed, is going to have a chi-square distribution with n minus 1 degrees of freedom. And so how do we go about that? Well, x sub I being normally distributed, so x sub I minus mu over sigma is standard normal. And so x bar minus mu over sigma over root n is also standard normal. And so the square of those is a chi-squared distribution with 1 degree of freedom. And so if I add them together, then I get x sub I minus mu over sigma quantity squared with a chi-squared with n degrees of freedom. And so it's beginning to look like the expression that we had just in our previous theorem. And so here we go. Now we're going to use the previous theorem. So our x sub I minus mu over sigma quantity squared, the sum of those, we can write as n minus 1 times the sample variance over sigma squared plus x bar minus mu over sigma over root n, that squared. And so what we've got, the two expressions on the right are independent. The moment generating function on the left hand side we know has a chi-squared with n degrees of freedom. The moment generating function on the right, we know the one of them has also a chi-squared. And so we've got a chi-squared with n degrees of freedom, a chi-squared with 1 degree of freedom, and our kind of unknown moment generating function kind of sandwiched in the middle because those two are independent. And so if we divide over, we see that our unknown moment generating function will also have a chi-square distribution with n minus 1 degrees of freedom. And so this is actually kind of an important thing, that now the sample variance doesn't depend on the parameter mu at all. It only depends on the parameter sigma, and is a function of our n-1 or n data points. And so because the moment generating functions determine the distributions, then sure enough, our expression is distributed as we said that it was. So why this will end up being an important theorem, an important property when we're talking about our inferential statistics. If we have something that's distributed normally, and maybe we want to determine what the parameters are, or we want to get a probability on the certain parameters, well, in order to do that, we need to be able to kind of separate them out. And so what this theorem does is give us a way of kind of relating some sample data to being able to find maybe a guess for what our true variance is going to be for a system with a certain probability. So we'll see a little bit later, probably coming up in a few videos, how we actually apply that theorem. So here it is. Don't forget it. Go over, work through all of that algebra, and I will see you all next time.